Okay, welcome back. This is a continuation of section 15.2, which is double integrals over general regions. And so this is the example 5 where we stopped. So let's go ahead and go over this one. Example 5 says, can you find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 0, and z equals 0? There's a few things that were not given to us. For example, they didn't really give us the two equations where it's bounded. We know that it's bounded by the tetrahedron, by the following planes, but we don't have the actual equations. Okay, so I'm gonna start with this piece right here. So they have given us this piece, not the x. Let me go ahead and go back. So me up to here. And so I can solve for z. So if I solve for z, then that would be 2 minus x minus 2y, because this is a function of xy. And so then that would be basically the function that will go in the integral. That would be the function that will go inside there. Okay, now, how can we find the equations? The equations are not given, and we'll go ahead and remember from the past video that they had given us some sort of regions like y equals x minus 1, y squared equals 2x plus 6, but we don't have that in here. When they don't give it to us, we have to find them. We're gonna have to find those equations. Okay, so for example, in this case, what happens if I say let x be equal to 0, and if I plug it into the green equation, then I get 2y plus z equals 2, and that will give me one equation. If y equals 0, then I am going to go with, let me go ahead and do z first. The order doesn't matter, but I want to follow that. If z equals 0, then I get x plus 2y equals 2. And if y equals 0, then I get a third equation where x plus z equals 2. And so we have all these unknown variables. But what if I want to use my equation 1 and I want to substitute equation 1 into equation 3? So I want to substitute my equation 1 into my equation 3. Okay, so my equation 1 is this one, and I'm going to substitute it in here. And so then that will be, okay, my equation 1, I'm going to plug it inside the equation 3. So equation 3 happens to be this one. And I got to solve for one of these letters, okay? So let me see, let's do 2 minus z. And so I want to replace the z. So we're going to solve for z. If I solve for z, then that will be z equals 2 minus 2y. And that's what I'm going to do here. Okay, so then that would be x equals 2 minus 2y. I do get 2 minus 2 plus 2y. And so I get x equals 2y. And this is actually a good thing. Yeah, this is one good thing. This is one good thing because I have created one equation in terms of x and y only. Okay, now playing around with these equations, I want to be able to come up with another equation. Okay, what if we use equation 2 by itself? Since equation 2 already has x and y. So x plus 2y equals 2. Let me go ahead and solve for y. So then that would be 2y equals 2 minus x divided by 2. Y equals 1 minus 1 half x. And I have another equation. So it's like I have two different equations. And both of those equations are in terms of x and y only, which is good. Okay, so now I have the two equations. Okay, I need those two equations. Okay, so now we have the necessary equations. So the equations are x equals 2y and y equals 1 minus 1 half x. All right, so go ahead and graph them and find the point of intersection. So if we want to find the point of intersection, let me see. I'm going to substitute this one into here. So I get y equals 1 minus 1 half times 2y. And when I do, I get y equals 1 minus y. 2y equals 1. So y equals 1 half. I get y equals 1 half. I'm going to plug it into the first equation. X equals 2y. And so x equals 1. So I have one point where they cross. The point happens to be at the point 1 comma 1 half. Okay, now let's go ahead and do the sketching. I've been assigning you guys the sketching because you should know how to sketch on your own. Okay, I have two different linear functions. And so this one over here is y equals 1 half x. So the origin, and then go up 1 and then to the right 2. And I have this. And then, okay, let's go ahead and do the other line. So then for the other line, we know that intersects at 1. And then it's minus 1, then to the right 2. So it's over here. Okay, we have this. The point of intersection. I'm sorry if this is not exact. My picture is not exact. I can do a better job with my graph. Let me go ahead and make it a little bit bigger. But my graph eventually, it's going to cross. It's like zooming in, okay? It's gonna cross right here. And the point where they cross is the point 1 and 1 half. And it's also bounded by x is equal to 0. So we're talking about this region right here. We know that it's bounded by x is equal to 0 because it was given to us. So it's bounded by x is equal to 0. And the two equations that we have in yellow, this one and this one. So it gives us what we have right here. Okay, and that's the point of intersection between the two lines. Okay, now you have to know which line belongs to which one. Okay, and so I'm gonna label this one in green. This line happens to be the line y equals 1 minus 1 half x. And this other line, I'm going to label it in pink, y equals 1 half x. Okay, now we had to think of the setup, okay? Okay, so now I got to think of the setup. Which one would it be the best setup possible? And so the function would be this one. 2 minus x minus 2y, and I got to decide. Do I want to do it with respect to the y's or the x? Which one do I want to do first? It's a selection that you yourself, you will have to make on your own. So I'm going to do the y first. And so then this will be y equals, then dx. And x is between 0 and 1. Okay, so let's go ahead and do y equals, so my first function for the y. Okay, give me one moment. Okay, so if I want the y first, then that, go ahead and look at your notes. If we want the dy first, then we're talking about type 1. Okay, so in this particular case, I'm selecting the type 1. And so that means that I will go in and then out. So we will go in through the pink. So 1/2 x. And then we will go out through the green. 1 minus 1/2 x. So like this, we're coming through here, yeah? Yeah, there's no easy way out for these ones. All right. I wouldn't want to do the other one. Because if I wanted it to do the other one, the type 2, if we want to do the type 2, for example, very quickly, you will have 2 pieces instead of 1, okay? Because this is a quick side note. If I wanted it to do the other one, I will have to come in through here and then exit through the pink, come up through here and exit through the green. So we will have to have 2 different setups if we want to do it the other way around. And so if that was to be the case, then, you will have to have 2 different integrals. Okay, so here we go. Okay, so then the volume will be equal to 0 to 1. We are integrating with respect to the y. So this will be 2y minus xy minus y squared from this function to this one, dx. Plug it in. We're replacing the y's. 2 times 1 minus 1/2 x minus x times 1 minus 1/2 x minus 1 minus 1/2 x squared minus 2 times 1/2 x minus x times 1/2 x minus 1/2 x squared. Okay, go ahead and work with the algebra. Okay, I'm gonna skip a few steps because it's a lot of work right here, but you're gonna have to do it on your own. And so I'm just going to go straight to the final setup when we combine all the like terms. So this is what I get. I get 1 minus 2x plus x squared dx. And now when we integrate with respect to x, this will be x minus x squared plus 1 over 3x to the third from 0 to 1. And you should get the answer to be 1/3. The volume would be equal to 1 over 3. Okay, this will be your volume. The algebra is not any easy. In terms of the test, for our test, I think I will be specifying which setup that I want. So I think that I will give you the problem. And then if I want you to create 2 different integrals, I'm going to tell you. Well, not necessarily tell you, but I think I'm going to tell you, go ahead and set it up in this form or go ahead and set it up in the other form. And I will let you know which way. The reason why I would like to do that, of telling you which way, is because I want to make sure that you can do whatever way I ask you to do. Okay, let's do the last one. We have the last one right here. Changing the order of integration. Fubini's theorem tells us that we can express a double integral as an iterated integral in two different orders. Sometimes one order is much more difficult to evaluate than the other, or even impossible. The next example shows how we can change the order of integration when presented with an iterated integral that it's difficult to evaluate. Okay, so in this particular case, they're given us the integral right here, and they want us to integrate this with respect to the y. But not possible to integrate with respect to the y because we have a sine y squared. What can we use? Can we use u substitution and do y squared, but then du will be 2y? That's not going to help. What can we use then so we can evaluate the integral right here? So in this particular case, this one will not be possible for us, okay? So we cannot really do it directly. And so let's go ahead and interchange. Let's go ahead and interchange them. Make a little note, okay? So we cannot do it directly. So we are going to switch them. So notice how it's from 0 to 1 and then from x to 1. So I'm going to move them, x to 1 and then 0 to 1. Is it possible for us to have that one on the outside? Let me see. If we do that change, will it affect the integral? And we cannot really switch it the way I have it. And the reason why I cannot really switch it the way I have it, it's because I will have this letter X on the outside integral. So that's not going to help me. Okay. So if I do this, that's not going to help me because how can I evaluate later on if we switch them and we have a letter still there? So that's not really helping me. Okay. So this is no help. So then what else can we do? Well, what we can do is we can use whatever has been given to us. Okay, so this one, it's telling us that y is between x and 1. Y is between x and 1. So this means that y equals x and y equals 1. Okay, so that's what it's given to us. We can do the graph of that. Okay, y equals, I get a line that looks like this. And then y equals 1, I get something that looks like this. Okay, so I have a crossing point also. And well, if y equals 1, x equals 1, so then the crossing point would be a 1, 1. Okay, now, what else? What else do we know? We also know the x goes from 0 to 1. So x goes from 0 to 1. And this kind of satisfies the graph already of what I have. Okay, so then I think I'm going to do it this way. Okay, so I'm going to do that. And now let me go ahead and label my equation. So this is y equals x or x equals y, and then this is y equals 1. Okay, so now let's go ahead and set up the integral. Okay. So when I want to set it up, we have the function sine y squared and I want to pick the right one. Okay. And so the way we have it, let me go ahead and erase this. We don't need it. The way we have it, it's not working. Okay. So now we can switch them. So what I want now is I want to switch them. So this way it didn't work. So we want the x first and then the y. So the x, that means x is equal to, and x is equal to. Okay, so x will be equal to, all right, so in this particular case, then we are going to be doing x is equal to 0. And y is equal to, I'm sorry, and x is equal to y. Okay, and x is equal to y. X is equal to 0, and then x is equal to y. Now, I don't know if it's helpful to know the type. So in this particular case, it seems like we are doing which type. Maybe if you label the type that we're using, it might help you. Okay. So in this particular case, it seems like we're using the type 2. We're coming in through here, and then we're exiting through that function. So we're coming in through x equals 0, and then exiting through the x equals y. And dy will be, y is between, well, 0 and 1. And so it seems like if these limits right here, they didn't change for the y. They didn't change. Okay, so it seems like if we changed it, yeah? Okay, let's see if this is better, because the other one we were not able to evaluate. Okay, so now, let's see. Well, it's with respect to the x, so then this would be x sine y squared from 0 to y dy. 0 to 1. I'm going to substitute the y sine y squared. If I plug in the 0, it's just going to be 0. So then dy. So this is the only thing that I have to integrate. And I don't know about you guys, but I think this one's really nice because, because now we can use a u substitution. Okay. And so using a u substitution, that will be very, very helpful. So we can say, let u be equal to y squared. Du will be equal to 2y. 1/2 du will be equal to y dy. Okay, so then this will be 1/2 over here. This will be 1/2 sine of u du, yeah? In terms of the limits of integration, we can come back and we can substitute them in, yeah? So if y equals 0, then u equals 0. When y equals 1, u equals 1. So our limits didn't change in this case, but sometimes they do change. Okay. Oh, I put out twice, I put the 1/2. All right, so then the volume here, it's going to be 1/2. The antiderivative for sine happens to be negative cosine from 0 to 1. So this would be cosine of 1 minus cosine of 0. Cosine of 0 happens to be 1. And we don't know what cosine of 1 is. So then I can just leave it as negative 1/2 cosine of 1 minus 1. That will be the final answer. I can also distribute the sign if you want to. If you don't like the outside sign, we can also write our answer as positive 1/2, 1 minus cosine of 1. So either or, it's a correct answer. Okay, so there's times when you're gonna have to interchange because the way it was given to you, it was nice. It was not a nice integral. And so if that's the case, you are gonna have to move them around in the way we did here. Okay, we have some properties of double integrals. We assume that all of the following integrals exist for rectangular region C. The first three properties can be proved in the same manner as in section 4.2. And the general regions of the properties from follow for definition 2. We'll go ahead and go over them. For example, if I have the sum of two functions, inside the integral, we can separate into two double integrals, the sum of two double integrals. If we have a constant, this is a constant in the inside, we can pull out the constant, find the double integral, and then multiply by that constant, etc. These are the properties that you should be aware of. Okay. Last, set up both type of integrals. Okay. Set up both types. Okay. And choose only one of the setups and find the volume. That's basically what I want. But I want you to set both integrals. Okay. I want you to do the setup for the type 1 and for the type 2. And then I want you to choose the right one and evaluate. I want you to do the same thing for this other problem. And if you need any help, go ahead and send me an email letting me know that you have questions from section 15.2. You can also send me an email telling me, Professor, can you check the work for the last two problems that you assigned us? And if you do send me that email, because I already have the work done for these two problems, I would like to check your work, and then I can say, oh, yes, you did a great job. You're doing good. Keep the nice work. Yes, the setups are right. Or I can let you know where you're doing it wrong. Okay, we're completely done with section 15.2, which is double integrals over general regions. Have a great day. Take care. Bye.